Hello, for today's video lecture we're going to be talking about kinetics in rigid body fixed axis rotation systems. So for this we are still using Newton's second law and kinetics, and so we build directly on Newton's second law, which states that force is equal to mass times acceleration, and rigid body we've got the m equals I alpha part of this as well. So moment is equal to mass moment of inertia times angular acceleration. If we put all our knowns, forces, moments, masses, mass moments of inertia into these equations, we wind up with what we call the equations of motion for that object. So by solving these equations, we can find either forces or moments given accelerations, or accelerations given forces and moments. All right, so for fixed axis systems, despite their simplicity, fixed axis rotation is very common in engineered systems. So something like this pitching machine, we are rotating about a fixed axis. Something like a hard drive is going to be rotating about a fixed axis. Something like a washing machine is simply going to be rotating about a fixed axis. These objects don't move except for that rotation. So with the mass moment, or with the moment equation, we are going to have to deal with a new term here. So m equals I alpha. With translation, we got to ignore our mass moment of inertia I, but now we can't ignore that because we are going to have some sort of angular acceleration. So we're not going to go over how to calculate that mass moment of inertia here. That's going to be in Appendix 2 of the mechanics map. But we are going to need to use that in our equation. All right, so fixed axis rotation systems come in kind of two types. We're going to have balanced systems and unbalanced systems. So a balanced system is where the body is rotating about a fixed axis at its center of mass. So this is our pitching machine was rotating about that. The center of the mass of that wheel is going to be the axis of rotation. Same thing with our hard drive. Our hard drive is rotating about its center point. So in these cases, the center point is not accelerating, so we have forces in the x is equal to 0, forces in the y is equal to 0, and the sum of moments is going to be equal to the mass moment of inertia times angular acceleration, and both of these are taken about the center point. So the center of mass / fixed axis of rotation, they're going to be the same point in this case. So m equals I alpha is going to be the one equation we are going to use for this type of system. All right, so in contrast to balanced systems, we can also have an unbalanced system. So in instances where a body is rotating about some fixed axis that's not at its center of mass, we're going to have forces and moments at play. The forces are going to be due to the acceleration of the center of mass in our system. So if you've ever had a washing machine and it's kind of got an unbalanced load, so the center is not exactly the center point, you can definitely feel the washing machine vibrating and kind of jumping around due to that unbalanced load. So sometimes it's unintentional, like a washing machine. Sometimes it's more intentional. So there are masses that are driven by small motors in a lot of video game controllers. You rotate that, you get kind of a vibration out of the system, and that's going to be definitely a on-purpose type system. So in these systems, we've got the center of mass, we've got a center point O, that's our fixed axis of rotation. Our center of mass is going to be some point off to the side, which is not located quite at the center. And in that case, we are looking at the acceleration of the center of mass, and the force in the r direction, and we're going to use r and theta directions here because of our spinning system, is going to be sum of forces in the r direction is equal to mass times acceleration in the r direction. Assuming the center of mass is staying the same distance away from that axis of rotation, m equals negative r omega squared. All right, so in the theta direction, sum of forces in the theta direction equals to mass times acceleration in the theta direction, and m equals r alpha, and here I've got it labeled as theta dot, theta double dot, so omega is going to be theta dot, alpha is going to be theta double dot, That is the angular velocity and angular acceleration of our body. All right, so, and as this spins, at any one instant, it's not going to be a constant force in any direction. The center of mass is going to be moving around the center, and that's why you get vibrations in these systems. As you spin them, that force is kind of constantly changing direction as it spins. All right, so for the moment equation, we've got two options. We've got m equals I alpha about the fixed axis of rotation. So we can take the moments and mass moment of inertia about that point. Or we could do the same thing about the center of mass, which is some distance away from that center point. So either one will work. The important thing is you need to be consistent. If you're taking the mass moment of inertia about the axis of rotation, the moments need to be about that point. If you're taking the mass moment of inertia about the center of mass, the moments need to be about that point. Just make sure you're consistent and everything will be fine with that. All right, so solving a rigid body kinetics problem, the process, just to review. So it involves 3 steps, just like our statics problems. Set up your free body diagram, draw the body separated from its surroundings, draw in all known and unknown forces. So again, for a balanced system, what's going to be important is the moments. For an unbalanced system, you also need to worry about that force because the center of mass is going to be off center. Draw in your acceleration vectors. So whether that is just angular acceleration or it is the acceleration of the center of mass as well. Next, you're going to set up, use your free body diagram to write out the equations of motion. So forces and moments, all of this. So break your forces down to x and y, or sorry, r and theta, if you are working with the unbalanced systems. And you can supplement these with kinematics equations. If you've got a way to relate the linear and angular accelerations, you can go ahead and add some equations that way. Once you have all of your equations, you simply solve the equations for any unknowns. All right, that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.